Hi and welcome to this HPE Aruba Networking AOS-CX 10.14 update. I'm Kamal Takodra, Technical Marketing Engineer in the Aruba Switching Business Unit, and today I'm going to be covering EVPN-VXLAN BUM replication using Underlay multicast. The agenda will consist of an overview, details of the feature, use cases, some configuration as well as further details, best practices, and then followed by a demo. AOS-CX 10.14 provides support for BUM replication in EVPN-VXLAN fabrics using a multicast underlay. This should be a single fabric with IPv4 in the underlay. The overlay supports IPv4, IPv6, L2 and L3 VNIs, and the BUM traffic of course will be confined to the L2 VNI. We support both VSX, VSF or standalone VTEPs in this architecture. The traffic types for BUM for the underlay replication are broadcast, unknown unicast, and well-known and unknown multicast. So it could be things like MDNS, VRRP, and other undefined multicast. Pin bidirectional is the underlay multicast routing protocol that we will be using. Pin bidirectional uses a *G formation using to build the multicast topology. Aruba CX VTEP switches actually become both the sources and receivers. Pin bidirectional scales better than PIM sparse mode when there's a many-to-many and highly distributed sources and receivers, which is the case in a fabric. All platforms in the fabric must support pin bidirectional for this feature to operate correctly. And also, all VTEPs must support replication mode multicast. There is no feature pack requirement for this enhancement. Supported platforms are as shown, and the platforms will be VTEPs when access and leaf. However, if the 6400, 8100 and 8360 are spine, aggregation and core, they will just be transit and not be replicating. Non-replication platforms, i.e. transit platforms in the fabric, can be the 8325, 9300 and the 10000, i.e. they're non-VTEP and can be spine aggregation cores. Now let's look at details on why use underlay multicast replication. We'll look at head-end ingress versus underlay replication. So head-end ingress replication is the default mode of operation for Aruba CX fabrics. For example, with ingress replication here, looking on the far left of the topology, with an ingress BUM packet, the source IP, which equates to the source VTEP, when having this BUM packet, needs to resolve destination IPs, and thus the destination VTEP VNI for each possible endpoint the inner BUM packet is sent. In our case, we have 6 VTEPs in the same L2 VNI, which means 6 packets encapsulated at the source VTEP. Finally, the splines replicate the packets to each VTEP. BUM replication increase is proportional to the VTEP/VNIs increases BUM flooding in the fabric. And the causal effects are that the increased bandwidth requirement at the spines an increased bandwidth requirement at the source VTEP too because of this replication, as well as source VTEP ASICs require more resources. Now let's look at the same scenario with underlay multicast replication. This time we have labelled the VTEPs and each VNI, which is VNI 5, which is mapped to VLAN 5 in this example. We firstly configure pin bidirectional in the underlay, and then we change the replication mode to underlay multicast. This makes VTEPs 1 to 7, VNI 5 and VLAN 5 join or get ready to join a multipoint tunnel 239.1.0.5. This will be covered in a bit more detail later. And as before, we have a BUM packet from a host on VTEP 1 in VLAN 5, which is VNI 5 in this case, hit the far left VTEP. With the incoming BUM packet from the host, which equates to the source VTEP and VNI, needs to resolve the destination IPs. However, in this case, it uses the multicast group IP to send the inner BUM packet once to the spine, as shown. The spines then forward to all the interested parties of the multicast group. So source VTEP replicates BUM type traffic to a single multicast address on the same VNI, as we just showed. And the causal effects are that the decreased bandwidth at spines compared to head-end ingress replication here, and we have a decreased bandwidth at source VTEP compared to head-end replication 2, and also the source VTEP ASICs have a decreased resource requirement too. Overall, this lends itself to enable right-sized designs and improve capacity and scaling of single fabrics. So the use cases here are to transition either a DC or a campus fabric to underlay replication, and it provides us a deterministic control of BUM traffic. It's more efficient use of switch resources, it lessens the burden on source VTEPs, and in terms of scale we can improve and the link usage is reduced. So let's go over some of the configuration and details. We'll only configure partial configs for brevity, but we can find these in publicly available resources. So the first step is to enable pin bidirectional, and this must be enabled in the default VRF. Please refer to the 10.13 release update for pin bidirectional configuration that I covered previously. Now the next step is to have EVPN-VXLAN operational in a single fabric, and this is actually interchangeable. You can set this up first and then have pin bidirectional operational. So step 1 and step 2 are interchangeable. The third step is to add multicast replication to the relevant VTEPs. So this is done under interface VXLAN. You add the replication mode and define underlay multicast. To revert back to ingress or head-end replication, there are two options. There's a replication mode ingress, or you can type no replication mode underlay multicast. The second part of the configuration provides an optional multicast routing protocol to be used. At this moment in time, pin bidirectional is the only option. We can then specify a flood group range, and the default range is 239.1.0.0, and we'll use this throughout the examples. You can change the flood range to your own range to ensure there is no clash with an existing multicast group that is configured. Now let's continue around configuration details and understanding further the flood group range. So 239.1.0.0/24 is a privately administered scope, and this is the CX default which is used for the flood group range. Now CX switches auto map VNIs to multicast flood group addressing, and this is for simplicity. There are 256 hardware entries available. Although the group range can be changed to customer requirements, this would mean changing the default group range on every VTEP. There's also a possibility to override the auto mapping. Is also possible at each VNI. And if this is done, then this must be modified at each VTEP and VNI. Best practice when using the flood group range, it must not be used in any other part of the fabric, either in the underlay or the overlay. Now let's look at the configuration in a bit more detail. So VNI 3 is mapped to VLAN 3, and this auto maps to 239.1.0.3 in CX for auto mapping. Then let's look at VNI 180, which has been mapped to VLAN 180, and this auto maps to 239.1.0.180. And if you recall, I said we had 256 entries available. So when we start revolving and adding more VNI and VLANs, we start reusing the multicast addresses. For example, VNI 259, which is mapped to VLAN 259, also uses 239.1.0.3. Now we can also see this by looking at VXLAN multipoint tunnel briefs, and we can see that VNI 3 is mapped to 239.1.0.3, as well as VNI 259 is also mapped to 239.1.0.3. And for simplicity, I've provided a table which shows all the VNI to multicast group mappings, and we can see, for instance, that 239.1.0.1 is mapped to VNI 1, 257, 513, 769, and so on, all the way down. We can see that 239.1.0.255 is mapped to VNI 255, 511, 767, and 1023, and so on and so on. So let's continue understanding flood group range further. So as I said earlier, the overriding the auto mapping is possible at the VNI level. But if you do this, then it must be changed consistently throughout the whole of the fabric. We did see earlier that the same multicast group addresses using the same hardware entries. Now this is accepted design, and the network will operate as expected. We may get some packet in discards, however functionality and operation is not impacted, and we'll cover this briefly now. So in this example fabric, we have VLAN 3 and 259 on each of the VSX VTEPs, and the standalone VTEP has VLAN 3. However, a broadcast packet arriving on VLAN 259 would also be seen at VLAN 3 because they share the same multicast group address. However, this will not impact the functionality or operation of the network. We can also see that this partial stretch of the VLANs and the sharing of the multicast group for VLAN 259, which is 239.1.0.3, and for VNI 3, which is 239.1.0.3. Now it's also possible, as we said, to override, and we can do this by a new command in the Ingress VLAN context. We can change the multicast flood group, and in this case we're going to change it to 239.1.0.99 for VLAN 259. If we now look at the multipoint tunnel, we can see that VLAN 259 or VNI 259 has now been allocated the multicast group 239.1.0.99. The alternate method is to have a different VNI to VLAN mapping, and will depend on the customer's methodology. And here we map VNI 99 to VLAN 259, and this means that multicast group 239.1.0.99 is mapped to VNI 99 but is mapped to VLAN 259. For correct operation, all auto mapping and overrides must be consistent across the whole of the fabric. Now let's look into further detail around underlay replication and multipoint tunnels. So we now have a new interface called a multipoint tunnel, which is created automatically when you enable underlay replication. So the source VTEP forwards the packet to this multipoint VXLAN tunnel. And in fact, the overlay packet is encapsulated and decapsulated in multicast packet at this point. And this is how the source VTEPs act like both multicast sources and receivers. There's no IGMP or MLD configuration required. It's all done automatically. So if we look at this show IP M route and look at it in a bit more detail, we can understand it a bit better. So first of all, we've joined this auto group 239.1.0.180, and we see that our incoming interface is our VXLAN 1 multipoint tunnel. And we're also forwarding on a uplink 1152. So this is effectively the switch acting as a source side. Then if we look further down, we again see the same group address. However, this time we have an incoming interface, and this is again the same interface, 1152. And then we're forwarding on this VXLAN multipoint tunnel, and this is us acting as a receiver and sending it out to the local VLAN. So this is effectively the source and receiver action and the internal multipoint tunnel in action. Now, very important to understand is we have these hardware tunnels created, and if we look at the multipoint tunnel brief, we can see the specific hardware tunnel that is formed. So we see the source VTEP, we see the destination, which is the multicast group address, and we see the associated VNI and VLAN. Just looking at other parts of the multicast tree, and this is just a quick snapshot. Looking at the rendezvous point, we see a building of the bidirectional tree, which is data driven and is formed when the multicast traffic is flowing. And you can see that this is a spine, and we don't have any multipoint tunnels here. We just have the normal M routes that you would expect to see, with associated incoming and forwarding links. Next, I want to cover VSX VTEPs with ROP. So when we're using underlay replication, VSX VTEPs support both multi-chassis lag and ROPs. With the multi-chassis, you'd have SVIs configured, but we're just going to focus on the ROP configuration. So we have a spine here, just a segment of network, and one VSX VTEP shown here for simplicity. From a upstream device perspective, when we have ROP configured, the upstream device or the pin bidirectional device will see two independent pin bidirectional endpoints effectively because of the layer 3 routed interface. Now, if that was the case, what would happen is for replicated packets, this will cause us duplicates and loops in the underlay back to VSX. So if there's a replicated packet here, it will come upstream and then go down here, and likewise. So to not have this behavior, what we do when we're having VSX VTEPs with ROPs and we have underlay replications, we do not form hardware tunnels, which is typically removed from the secondary member of the VSX pair. And this is to remove duplicates being sent and spinning around the network. So, very similar situation. I've shown the output of one of the VSX pairs, the primary, and we have the in-cap, D-cap, and the VXLAN tunnel interface, and we also have the hardware tunnel. However, when we look at the secondary, we have no hardware tunnel or entry formed, and also we only have the source side showing on the secondary, where the incoming is the multipoint tunnel and going upstream on the uplink, but there is no pin bidirectional formed properly, so we don't get the duplicates. And on a failure of the ROP or the primary chassis, the secondary would take over and the hardware tunnel would be formed and traffic would flow once the PIM tree is formed. So let's go over some of the best practices. Some of which I've covered already. So really don't use the flood range in any other part of the fabric. It's not expected to actually stop the functionality. It's more of a behavioral and operational issue. It becomes harder to troubleshoot, so we recommend not to use the multicast flood group range anywhere else, or use a So let's cover some of the best practices. So the first thing is don't use the flood range in any other part of the fabric. Although it's not expected to impact functionality and behavior, it's more of an operational issue when it comes to troubleshooting. It becomes very difficult if you've got the flood group range and that same multicast group being used elsewhere. So you always need a spinal core. A transit is required, because what we're doing is we're moving the replication away from the access VTEPs and really moving it away to the core. So again, do not attempt a direct connection between VTEPs to VTEPs. We do need a spine or core, which is required in this single fabric scenarios. So when it comes to VSX VTEPs, we can use MC lags or ROPs, but you must not mix that on the same VSX VTEP because of the ROP rule that I described earlier. It would confuse a system if you did that, and really we don't see that typically in deployments, maybe in a test lab. So stick to one or the other when you're using VSX VTEP. In terms of configuration consistency, that's really important. So we do say if you are going to change things, then the flood range must be the same and consistent across all VTEPs. Otherwise, you may experience some packet loss. Again, the same with auto map override must be the same across all VTEPs. So now for a short demo. In this topology, we're going to review EVPN-VXLAN ingress replication versus underlay replication. In this topology, we have three VTEPs. VTEP 1 at 192.168.1.20 on the CX6300, and VTEP 2 192.168.1.159 on the CX6300, and then finally VTEP 3 at 192.168.1.160 on the VSX pair. Each VTEP has a layer 2 VNI 180 on VTEP 1, VTEP 2 and VTEP 3, and we'll be using VNI 180 throughout this demonstration. VTEP 1 will be the source VTEP in all cases. 4 broadcast frames will be sent from a host generator on VTEP 1. We will then compare ingress versus underlay replication in 2 scenarios. Let's kick off with head-end ingress replication, and now let's start packet trace on the VTEP. And from our host generator on VTEP 1, we're going to send 4 broadcast frames. Now back to the packet trace. The 4 broadcast frames generated 8 frames at the source VTEP for stretched VNIs. That's 4 frames times 2 VTEPs, which equals 8. So the replication is proportional to the number of VTEPs across the stretched VNI. Taking a closer look at the first frame, we see source VTEP 1 1.20 sending to VTEP 2 at 1.1.59. Further examination of the frame shows that this is VNI 180 and it's a broadcast destination, all Fs. Looking at the second frame, we can see source VTEP 1 at 1.20, this time going to VTEP 3 1.160. The second frame sending to VTEP 3 is also related to VNI 180 and broadcast destination, all Fs. This cycle is repeated per broadcast frame. Source VTEP frame replication increases with the number of VTEPs in a stretched VNI. Now we're going to change to underlay replication. With PIM bidirectional operational, we now add underlay replication to all VTEPs using the replication mode command. Aruba CX auto maps all VNIs to specific multicast addresses. In this case, our interest is VNI 180, which is mapped to 239.1.0.180 for our quick tests. Let's start off with the packet capture again. Now let's send the 4 broadcast frames from the host on VTEP 1. Now back to the packet capture. Only 4 frames are sent by the source VTEP1. We now have a one-to-one mapping of broadcast frames. On closer examination, we see source VTEP1 1.20 is now sending a frame to 239.1.0.180 for VNI 180. Further examination shows that this packet is indeed VNI 180 and broadcast destinations all Fs. The second broadcast frame from source VTEP1 1.20 also sends a frame to 239.1.0.180 for VNI 180. Again, the packet detail shows VNI 180 and broadcast destination all Fs for this packet too. The cycle is repeated per broadcast frame. Frame replication is only sent once per source VTEP per VNI stretch. This method reduces the processing requirement on source VTEPs and helps reduce the burden on the source VTEP in these situations. I hope that is useful and informative to you, and thank you for watching.